welcome back everyone. Today we're going to be doing AP Calc section 1.8, the squeeze theorem. So the squeeze theorem is just a theorem that helps us solve limits in a kind of intuitive, unique way. Let's say that we're trying to find this limit of f of x as x approaches some value a. If I can show that the function f of x sits in between a g of x and an h of x, two other random functions, whatever they may be. If I can show that this f of x sits in between those two functions, and I can also show that both these functions, g of x and h of x, go to L as x approaches a. What this allows me to do, and it's kind of intuitive, we have two functions, a top and a bottom function, g of x and h of x. And they both approach the same value in the range. So if f of x is in between these two values, what this has to mean is that the squeeze theorem is saying that f of x is so squeezed in between g of x and h of x, it has to also go to the same value. And this is what we have here in this little diagram. Let's say g of x is this orange function that we have right here drawn out. And we also have the green function, h of x is the orange function, and g of x is the green function. And let's say f of x is this blue function. If I know that g of x is a bottom function, and h of x is this top function, and they both come to the same value L at x when x approaches a, well, given that f of x is in between these two, it has to also get squeezed in between. The only place it can get in between that also gets there is L as well. That's why the limit also approaches L. Here's a quick example using the squeeze theorem to find this limit of f of x as x approaches 0. So we're given the fact that f of x sits in between these two functions. Now by our diagram, we can kind of think of this as the green function g of x, and we can think of this top function as h of x. And we can show that the squeeze theorem applies if we can show that both the g of x function and h of x function both approach L as x approaches 0. And let's do this graphically. If I have a graph here, we know what negative x squared and x squared plus 1 look like. It's going to be negative x squared plus 1 is going to be the quadratic function like this, and I'll do it in green. But because it's plus 1 in the range, we have to move this thing up 1. And with the orange function, h of x, what we have to do is we just do the opposite, where we've just flipped the quadratic because it's still getting shifted up 1, but there's no negative to flip the quadratic. So whatever this f of x is, we don't care what it is necessarily in this example. Whatever it looks like, as it gets closer and closer to here, it has to stay in between these two. And if you look at the graph, it is clear that the limit as x approaches 0 of negative x squared plus 1, we can also use direct substitution. It'll be negative 0 squared plus 1. And then the limit as x approaches 0 of x squared plus 1, that's going to equal 0 squared plus 1. Both of these equal 1. So by the squeeze theorem, because we know both our limits of the top and bottom function go to the same value, f of x has to be squeezed in between, which means that the limit of f of x as x approaches 0 is equal to 1. Here's another example on how we can use the squeeze theorem to find a more difficult or trickier limit. If we try and use direct substitution to solve this limit, we'll get 0 squared sine 1 over 0. And this is kind of funky because do we multiply everything by 0, make it 0? But what about this division by 0 as well? What are we going to do with that? So we're going to have to use the squeeze theorem to solve this one. We know that sine function, no matter what's the input, is always going to be in between negative 1 and 1. So I can say that the sine function is less than 1, but it's bounded below by -1. And because it's 1 over x, that's what we'll put in there. Now we can multiply all three of these by x squared. And what we've done is we've constructed a lower function and an upper function that we can use to finally use the squeeze theorem on. So we'll have negative x squared is less than or equal to x squared sine 1 over x, which is less than or equal to x squared. So by solving these limits by direct substitution, we can see that the function that bounds x squared sine 1 over x above and the function that bounds x squared sine 1 over x below both can squeeze x squared sine 1 over x by 0, because both the limits get really, really close to 0 as x approaches 0. So what this means then is that because both limits went to 0, the original limit we're trying to find equals 0 by the squeeze theorem.